Hello ladies and gentlemen, this video dedicated to discuss rheology. First we'll start with definition of rheology. Rheology is the science or the study of deformation and flow of materials. We need to study rheology in drilling fluids for many reasons or for many purposes. First, to determine chemical composition, to determine mixing procedure, to determine testing procedures, calculate fluid law model and fluid law regimes, assess friction pressure, and estimate ability of a fluid to carry and suspend cuttings. Finally, to evaluate hydrostatic pressure and the equivalent circulation density. There are some factors that affect the rheological properties. We'll start with solids. Once the solids content in drilling fluid more, so in this case the rheological properties will be high, and there will be higher stress to break the solid aggregation. Surface area. If the surface area of the chemical composition or the major components of drilling fluids higher, then they will react more rapid. So the reaction here will create coagulation due to the bonds among the particles. In this case also, we will need yield stress to break the coagulation and commence flow. Contrarily, the opposite, if the surface area is less, the interaction will be slow and the drilling fluids will tend to be more thinner, so the rheological properties here less. Composition, water, chemical addition, if the percentage or ratio of water is less, then the properties of fluids will tend to be higher in rheological models. Contrarily, if the water ratio is more, the rheological properties will be less and the fluid tends to be more thinner. Depends on what sort or what types of chemical products need to be added to mix a fluid or to mix water to make fluids. Then every material will have its ion interaction and electrostatic forces. The coagulation depends on types, water percentage. If the fluids more coagulated, there will be a requirement to add chemical products that have negative charge in order to disperse the coagulation. Mixing procedure and testing procedure. As we highlighted before, that the chemical have different interactions and different behaviors. So the addition of chemicals need to be in sequence and there should be procedures. Which chemical need to be added first and which chemical need to be later on, one by one. Also, that will determine what type of mixing energy, low or high, and agitation. For example, once we add pentonite or the materials that needs to prehydrate, we need to determine or to allocate a fixed time or a period for these materials in order to prehydrate very well. Before we commence with reading the rheological model by using rotational viscometer, we need to precondition the mud for 20 minutes. Depends on what degree of temperature required, if it is surface or ambient temperature or bottom hole circulating temperature. There are some parameters that can use to calculate or to define the rheological properties. First, shear stress. Shear stress, the force required to get constant flow. The symbol in Latin here, and the unit of measurement here, pound per 100 square feet. Shear stress equal to force per area. Shear rate, the rate of a changing velocity. Here the Latin symbol and expressed in reciprocal second. Viscosity, the viscosity measured in centipoise and indicates the resistance of a fluid to flow. It can be calculated by dividing shear stress by shear rate. Plastic viscosity, part of resistance to flow, but this sort of viscosity caused by mechanical friction. The symbol centipoise the measured in centipoise, and here the sample of this plastic viscosity. Apparent viscosity. Viscosity of fluids measured at a given shear rate at a fixed temperature. Symbol is here, and also unit of measurement centipoise. Yield stress or yield point. The initial resistance to flow caused by electrochemical forces among fluids particles. Symbol in Latin here, or we can abbreviate yield point by Y and P. It measured also same as shear stress, pound per 100 square feet. Last parameter, gel strength. Gel strength, the attractive forces among fluids particles under static condition only, and it also called gelation. It measured as same or similar to yield stress or shear stress. We have two types of fluids, Newtonian and non-Newtonian. Non-Newtonian has 4 different types, or can be categorized to 4 different fluids: plastic, zetoplastic, dilettante, and thixotropic. We will commence first with Newtonian. Here is the consistency curve of stress and rate. This line is the viscosity. We can see from this figure, viscosity started from 0 means there is no, or there will be no shear stress value. Stress 0 and no yield point. That means the fluid will commence to flow once we start applying only the minimum shear stress. Then the relationship between shear stress and rate is proportional relationship, and viscosity will be constant, no changing. It has a single value. 4 types of non-Newtonian fluids. Here is the curve, consistency curve of plastic fluids. We can see the same here. Viscosity constant, it is a straight line, there is no changing, it has a single value regardless of rate. And the relationship between rate and yield stress is proportional, but there is here a minimum or a fixed value to be applied in order to get flow. So the fluid here need this value to be applied prior to commence flowing. This value is called yield point or yield stress. After this point, we can see relationship is proportional between rate and stress and viscosity constant. Zetoplastic fluids, here is the figure, consistency curve. We can see here viscosity started from 0. That means no shear stress value or no shear or no yield stress, no yield point. And we can see from the figure the viscosity is not constant, so it is changing because the curve is not straight line. So the relationship between rate and viscosity is inverse relationship. Once the rate is higher, the viscosity will be lower, but will never go to 0. Until this, then viscosity will keep at the minimum value regardless if the rate increased or decreased to this optimum value. But if the rate get slower, more slower to 0, viscosity will be increased. This property called shear thinning. There is no yield point and no gel strength development. The third type, dilettante, same as zetoplastic, but the difference in the property type, we can see viscosity is not constant, it is changing. It started from 0, there is no shear stress, there is no yield point, but here the opposite. If the shear rate increased, the viscosity will increase, and this property is called shear thinning. The last type of a fluid, thixotropic fluids. So we can see here there is a yield point, same as zetoplastic, but the difference, there is a yield point. We can see here if the shear stress stopped, then this fluid will tend to develop gel strength we can see here the return to the second value of gelation. The relationship, it is inverse between viscosity and rate. Viscosity not passing from the origin point or from zero means this type of fluids has the property of gel strength development, and it has a fixed point needs to be applied to fluids in order to commence flowing, this value called yield point. Now we will start with studying rheological models. There are 4 different types of rheological models. We need to study the models in drilling fluids for several reasons to simulate the characteristics of drilling fluids and the behavior under dynamic condition, and also it is used to calculate or to predict, to estimate the equivalent circulation density downhole, and to see the efficiency of drilling fluids for well cleaning, and also used to calculate friction pressure in the annular. We can get the rheological properties that needs to be attained or to be achieved in order to allocate or determine what is the appropriate rheological model for this sort or this type of fluids, from Ty, gel strength value, relationship between shear stress and shear rate. We can get all of this from a mathematical calculation from the curve of a lab or from a reading of rotational viscometer after preconditioning the fluids, and from 3 to 600, these 8 readings, different readings, will be required in order to determine the parameters or the values of parameters that needs to be understood in order to define what is the appropriate rheological model. Here there are 3 different flow regime. The first one is plug. We can see the velocity is very slow, but it is equal from center and at the walls of the pipe. This when the rate is very low and the property of fluids gelatinous or it has gelation. Transition zone here, 12 start or 12 transit to second regime. Second regime is a laminar property of this regime. As we can see from the figure, in the center it is more faster than the walls of pipe. In order to study the behavior of fluids to be in this flow regime, we need to apply one of the 4 different rheological models. The last one, turbulent flow, we can see here it's more faster and the velocity is equal in the center and on the walls of the pipe, but the direction it's not equal. It has a different or it has irregular and it is in a state of turbulence. Therefore, it is hard to understand fluid behaviors and describe its fluid model. Either, in order to describe behavior of this fluid, we need to apply 1 or more, 2 or 3 modules to get the behavior of fluids to be pumped or to be flowed in this regime. Here we can see, in general, the 4 different types of rheological models. Newtonian. These 2, they have the same property, but they are different. There are some differences between them in terms of viscosity property. Shear thinning here and shear thickening here. Both it's called power law. Here Newtonian, power law, Bingham and Herschel-Balkley. We'll start with Newtonian. Newtonian we described before. It commence flowing as soon as the shear stress applied. Shear stress 0, no yield point, no gel strength development property. Slope here it's called viscosity and it is constant straight line. It can be calculated from dividing shear stress per shear rate. Example of this Newtonian fluid can be designed or can be described to simulate or to predict behaviors of Newtonian fluids. Example of Newtonian fluids: water, gasoline, light oil, sugar and salt solution. This is the first one that can be simulated or can be used to calculate properties of fluids. Bingham First one for the non-Newtonian fluids. We can see it is simulating, or it is predicting behaviors of plastic fluids. There is yield point, but here the slope of viscosity called plastic viscosity. Plastic viscosity can be calculated from reading of 600 rpm and 300 by subtraction between them. This fixed point can be calculated by subtracting reading of 300 rpm minus plastic viscosity. Example of this, as we said before, plastic fluids. The second one, power law model. Power law can predict behaviors of zetoplastic and dilettante. At the same time, can be described by this equation: yield stress equal to K multiplied by shear rate, and the K is consistency unit, and N, it is the power law exponent. So the relationship here we can get from by calculating the N. Fluids that equal to 1, it is Newtonian. More than 1, dilettante, and it has shear thickening property. Less than 1, zetoplastic, and it has shear thinning property. Examples of this: polymer, mud, soap, paint, and grease. These all examples for zetoplastic and dilettante. To sum up, power law, it is used to predict fluids behavior, and it gave accurate simulation or accurate values only if the rate is slow, but there will be drawback if the shear rate is higher. Last model, Herschel-Balkley. It is the same as Bingham, but the difference here, the viscosity is not constant, and it is same as power law model, but it is not moving from origin or from zero. There will be on shear stress curve fixed point to be applied prior to commence flowing. It can be calculated from this equation: shear stress equal to yield point plus K multiplied by shear rate exponent of N. As we said in the power law, K is the consistency unit of a fluid and power law exponent. It can be calculated N and K from reading of 600 and 300 rpm. Curve not passing from origin. That means there will be yield point, and fluids here tends to develop develop gel strength if the fluid in static condition. There will be reading for shear stress even if rate is 0. Herschel-Balkley, it is a developed model of power law, and it can well predict behavior of fluids in both cases. If the rate shear stress low or high, it can predict the behavior. Can be used to calculate friction pressure, equivalent circulation density pressure. That's why it is preferred to be used to calculate behavior of fluids that have more viscosity, or gelatinous fluids, for example cement or spacer fluids, drilling fluids that has clay such as bentonite. We reached to the end of rheology.